Greetings, the Astro 30 here yet again, looking at more experimentation. Today we're going to look at a follow-on video from the one I did before with a series pass regulator using an error amplifier. In this video we're going to look at implementing constant current, adjustable constant current. Now this is a pretty standard way of doing things. Ignore this transistor part for the moment. Now we're using an op-amp configured as a comparator. Now we have one side of our sense resistor or shunt connected to one input of the op-amp. The other side of the op-amp is referenced to, well, the positive rail here and the other side of the shunt. So what it's doing is it's comparing the voltage drop across this resistor with what this potentiometer is set to. Looking at the business end of this schematic, I'm using an NE5534. It can be any op-amp. I'm using the NE5534 because it has a plus minus 22 volt supply rail maximum. So I was planning on putting 30 volt DC through the positive rail with a minus 5 volt rail. So 35 total, which is within the limits of the IC's absolute maximum ratings. So you could get an adjustable power supply up to like 28 volt, for instance. But the way the comparator is working here, it's comparing what the voltage drop across this resistor is compared to what the voltage is set on that pot. So say we had this input pin here via this pot set to 10 millivolts, we'll say. Once the voltage drop across this resistor equals or exceeds 10 millivolts, then the comparator will saturate its output to the negative 5 volt rail. Now the way a comparator works is quite interesting. If we have a higher potential here on the positive input than we do on the negative input, say we've got 2 volts here and 1 volt there, then the comparator will saturate to the positive rail. So you'd have, say, 15 volts coming in here, and you'd have 2 volts roughly less on the op-amp's output here, 13 volt, unless you've got a rail-to-rail op-amp, of course. Conversely, if this input pin is now a higher potential than that input pin, so we've got 3 volts here now, and still the 2 volts there, then it's going to work in the opposite direction. It will then saturate to the negative rail, and it needs to be in bipolar configuration, and in this case we're connected on pin 4 to the negative 5 volt rail. So we would see minus 3 volt here at the output. Now this can be useful because then we can use this negative going output with respect to the common rail to turn on a PNP transistor to turn on a limit LED like it is here. And we can also go through the cathode of a standard rectifier diode so that we are only seeing the negative voltage minus 0.6 of a volt here, and we can connect that to our error amplifier, like say the bases of the output stage, and then it will clamp the voltage down at the base of the output stage but limit the current to, well, whatever the pot is set to. And in the case of a short circuit, like you've shorted the output completely, well, if this was at its minimum with these current resistance values, you would see roughly about 1 amp of current at the output, which is fine. And if this was at its maximum setting, probably 3 amps. This is good for 3 milliamps current limit to 3 amps. If you wanted, say, 5 amps of current limit total when the pot's at maximum, you could change this 56k to a 33 and change this resistor value down here for the shunt to a 0.33, and that'll give you a little bit more headroom there. Or conversely, if you want less current limit, That is, you want to set, say, a current limit of maximum of 1.5, 1.8 amps. Well, you could just simply change this shunt resistor to 1 ohm, and you would get, around about the 1.8 current limit mark when the iSet pot is at maximum. So I've got the comparator current limiter, or constant current, set up on the breadboard. So we'll have a look at the circuit and do some measurements and see how it works. So there's the comparator circuit built up on the breadboard using a single op amp, one channel of the op amp. The other side is configured as my voltage error amplifier, and output stage is connected off screen here. So it's all set up as it was in the first video with the error amplifier and output stage and pot and all that sort of stuff. But what I've got here is the multimeter probe is connected to the cathode end of the diode that comes off of pin 1, and we're going to measure the voltage at that pin and see what happens when we start loading the circuit. I've got a white LED here to indicate current limit. Could have used blue, but it doesn't really matter. So I've got a 330 ohm resistor there as our test load, and the current through that at 15 volts is around 45 mA. So that's a good starting point. Meter is set up, and I'll turn the main supply on, which is set to 15.6 volts. Currently we don't see anything because I haven't turned the 5 volt reference rail on. Reference rail on, and we got 14.398 volt coming out of the comparator. As we can see, the comparator has saturated to within a volt of what the actual voltage coming in is, which is 15.6 volts and bugger all current. So that's my current pot, so I'll just make sure it's rotated fully counterclockwise, which it is. I will connect up my load. Bam! Almost minus 4 volts. So it's now saturated to the negative rail within a volt, which is 5.5 coming in roughly. So that means that little circuit is working. And I don't know how well you can see that, but the LED is illuminated. So if I disconnect the load, the LED goes out. Reconnect. Oh, excuse me. There we go. And it's working. Now if I also conversely rotate the pot, the LED went out. LED on, LED off. LED on, LED off. So what we should do is do some voltage measurements on the comparator just to see what we've got. So with the potentiometer set just before current limiting and the 330 ohm resistor connected, I've got the full supply voltage from the main power supply going across one end of the 330 ohm resistor, and the negative side of the circuit is coming off of this shunt. Now if we measure on what the output side of the shunt is, which is our common rail, we're looking at roughly 31 odd millivolt there. If I was to measure what is coming out of the potentiometer going into pin 3 as our comparative voltage, well, it's more like 50 millivolt, which is right, and it's not in current limit. However, if I was to rotate the current pot until we roughly got to the 31 millivolt mark, which is about almost there, it's too far. It's very hard to set this type of pot to that sort of voltage. There we go, 31 millivolt. Current limit LED is on, and we are in current limit. So if we were to measure the voltage now across the shunt, so we've got 31 odd millivolt there at the shunt, and maybe a little less going into the op amp, but it's within a margin of error for the tolerances of the circuit. So that's exactly how the comparator's current limiting, or constant current, is working. So now it'd probably be a good idea to connect the other end of that diode, the anode, to our error amplifier's output stage, reconfigure the meter connection so we're measuring from the output now, and see how the circuit operates. Okay, the circuit's reconfigured, and we've got an adjustable output through the error amplifier. So for these tests I'm going to stick to around about the 5 volt mark, and it probably would help to connect not like that, but connect the output of the current limiter. So with the current limit still set to minimum, I will now hook up the 330 ohm resistor, and nothing actually happened. And I know why, the voltage needs to be higher. So I'll increase the voltage to 10 volt. Right, the current limited there. The current limit light is on. Output has reduced to 1.9 volts roughly, and the power supply is saying that it's about 100 mA current draw, which means this circuit is now limited to a 100 milliamp current draw. And I can increase the voltage pot and nothing happens. It still stays around about the 1.9 volt mark. So it's staying roughly at 1.9 no matter where I put the voltage pot. And that's exactly what we want. Word of warning here. I was doing some tests on Sunday with this current limiting circuit, and I had a slightly different configuration, and I ended up destroying a clip lead. Oh, I farted before I left the room and it still stinks, even after 5 minutes. Anyway, here is the destroyed clip lead here. As we can see, I might have to get a little bit better light on this subject. It's probably the best that I can get, the lighting and the focus. As we can see, it's literally melted the insulation. There was actually smoke pissing off this thing. And this wire itself should be good enough up to 3-4 amps of current running through it. So there was obviously a lot more current running through it than that. And it managed to blow up 2 transistors, an NPN and a PNP signal transistor, BC557 and 547 respectively. It shorted the BC557 completely out between base collector and emitter, because they got red hot. Smoke was pissing off of those too, and this was when I was actually shorting the output. So what actually happened? Well, I'll do up a quick drawing to simulate what was going on. So this is as best to my memory of how I had it set up. Got the shunt over here at the input side now and going into a comparator. That was a fixed comparator, which was actually limiting the output current originally to about an amp, which is fine. We're going through a PNP transistor here. It was also connected to an LED to that in common. We've got the error amplifier here in the output stage, and what I'd done was I then took, when this transistor turned on, was to make this NPN transistor turn on and effectively bring this base to the common. Now, during testing, that worked fine, and here is our 5 volt reference voltage for pin 4 of the negative side of the op amps. Initial testing, it worked fine. That meter was saying it was less than 0.1 of a volt on the output. The other supplier that's over there, it's turned off at the moment, was limiting down to about 100 mA. Limit LED was on, all was good. That power supply was connected to the positive lead, which was going to the negative terminal of the main circuit. And of course its negative was then going into the op amps. The smoke started coming off of that lead. This voltage shot up to roughly 19 volts, and then this meter for the amps, that really started pegging out. I didn't even capture in my brain how much current was actually coming through that meter. I'm pretty sure it was over 10 amps, because this meter was going crazy. It couldn't even keep up with what was going on, and then smoke was really coming off of that lead, and I'm like, what's going on? The lead was red hot, and basically I turned this into a heater, and I killed all the supply quickly. Luckily I didn't destroy the op amp, but I'm still trying to figure out what actually happened there. Why did it do that? Basically, when this output is dead short, I'm bringing the base of this transistor to the common, and that is now shorting between this negative rail, positive rail of this supply, and feeding back through there. So all the current was feeding back into the 5 volt supply, and it went into current limiting. But it was still pushing out probably close to 10 amps. So I surmise that possibly it was feeding back the short circuit voltage into the control pin or the adjust pin of the LM317T that's in there, and it just confused it. It didn't like it. And it didn't damage $200 worth of project there, but I did take the lid off, and the transformer that was in there was red hot. So it was dumping some current. So, word of advice, don't set up short circuit protection or current limiting like that. Yeah. So anyway, so the other supply is now turned back on, and my reference voltage is turned on, and I've set the potentiometer to around about 5.47 volts, and the current limiting pot is all the way at minimum. So I'm basically going to short the output now, and as I said, if you've configured it wrong, bad things can happen. So I'm going to short the output, make sure that I've got everything connected correctly, which I have. The voltage dropped well off to less than 10 millivolts, well, about 12 millivolts there. My 5 volt supply is not showing anything unusual, and the other supply is staying around about 100 mA. And the output is indeed shorted. And my limit LED is turned on. Whether or not you can see that, I don't know. So if I was to raise the current pot, the current over here starts increasing, and so does the voltage on the output. So I'm going to set this to 1 amp. We are still in current limiting. The LED is illuminated. It's still short circuited, but the leads are not getting hot. And I'll just move this soldering iron lead out of the way, and it's sitting roughly at 1 amp, going up and down a little, and we've got less than 0.6 of a volt on the output. This is exactly how current limiting or constant current should work. It lowers the voltage right down but keeps the current constant. So if I was to wind that control up further, well, yeah, why not? To say 2 amps now. Okay, we got 2 amps of current draw. The leads are not getting hot, but the current shunt is starting to warm up, and the leads coming off the other power supply are not hot. We're at 1.2 volts DC now, but still in constant current. So I'm going to wind this up further. I'm almost at the maximum of that current limit pot, exactly 3 amps of current draw. The voltage output has risen to around just a little over 2 volts. 5 volt power supply is still happy. Circuit appears to be happy, although I can see smoke coming off those resistors. I don't know if you can see the smoke coming off of it, but yeah, those resistors aren't quite adequate for the job. So to have constant current of 3 amps going through there, they're two 2-watt devices, and they're going to be, yeah, red hot. So I'm going to remove the short circuit now because I don't really need to keep it shorted. Everything else though, however, is okay. The output stage was starting to warm up. This driver transistor is slightly warm, so it could probably benefit from a heatsink. But the IC is not even hot, and neither was the transistor that's driving the LED. So the circuit was perfectly fine, apart from a shunt resistor. Right, so I should show the finalised schematic of what I've got here in the current configuration. I'm using an LM833 op-amp IC. You could easily use an NE5532 or 2 separate NE5534s. And the second one also connects to this negative 5 volt reference rail, so you can get down to 0 volts. This 470 picofarad here is just to keep this op-amp as stable as possible. And as we can see, the current shunt resistor is all the way over here with a line drawn back to show what connects to the common output side of the power supply. So one side of the op amp here is connected to the common, which goes to the load, and the other side is not. So that's how that is set up. Got the diode going over to, well, basically the output of pin 7, and I believe that's how I've got it configured. Yeah, it actually goes before this 1K resistor, so I might just quickly correct that, as badly drawn as that is. Yeah, so it's connected to the base directly here rather than the output pin of the IC. Got the voltage set pot over here, clockwise going in that direction. Keep it at 10K to give a nice variable range. Now, in the original circuit I was talking about putting a trimmer down here to adjust the 0 volt portion. Well, considering that the pot is wired backwards for all intents and purposes to the circuit, that's not going to work. So we would put the trimmer on the positive side. So you're actually, when this is all the way anti-clockwise, it's coming up to the positive, we can adjust that out to give us our 0 volts as desired. I'd keep that trimmer resistance lower than 2K. I tried 100K there, it's just too fiddly to try and get it to 0. It doesn't zero out properly, it keeps jumping up and down. So you could put some form of flyback protection diodes in here as well to protect the output, which is not shown on the schematic. The schematic can be greatly improved, but for what I've got set up, it does actually work, and it does deliver 3 amps quite happily. You could easily increase the amount of output transistors you've got to 2, maybe even 3, depending on how much current you want to move. And you connect all the bases and collectors together here, so the bases to there, collectors to there. And in the emitter, well, you put probably a 0.33 ohm resistor as a degeneration resistor, so that each emitter or each transistor is being balanced to handle the load equally. So you give a little bit of degeneration here on each emitter before connecting the other ends of the resistors together to the positive rail. So that's it in a nutshell. That's constant current in a power supply, which is how it should be really done, and in most cases that is how exactly it is done. So I hope you found that video interesting. Feel free to play around with the circuit, it works fine. It didn't explode. Would have been funny on camera if it did. I wish I'd captured everything I did on Sunday. It would have been epic to see that that lead smoking. Anyhow, I'm going to leave this video here. If you enjoyed it, please remember to go down the bottom there, rate, comment, subscribe if you haven't done so already. And this is the Astro 30 saying, as always, I'll see you in the next video. Thank you for watching. Have a great day.